In this next lesson, we'll continue to define and differentiate water quality terms, and the terms we discuss here will lead us into the next two lessons, which are in Excel, where we actually calculate some of the concepts we discuss. So that bottom one is the objective for the next two lessons.
You see a list of definitions here, and I want to go through each one and talk about what they mean and how they differ, starting with concentration. Concentration we've already talked about a little bit. Concentrations are a mass of a substance per volume, milligrams per liter, micrograms per liter. These are always defined in metric units like milligrams per liter. Sometimes you hear parts per million used as units on concentration. A concentration is something that is measured in a lab. Typically for a water sample, you take the water sample, bring it to the lab, analyze it, and the value that's given to you by your analytical equipment is a concentration, milligrams per liter, micrograms per liter. Concentrations are important because they're what we use primarily for our water quality standards, like drinking water standards, MCLs, maximum contaminant levels, are all concentrations. We also use concentrations for toxicity assessment and assessment of toxicity for compounds that can be acutely or chronically toxic. Next up is flow rate. Flow rate is an instantaneous rate of water passage. For example, flow rate of water leaving a tile outlet. The units here are volume per time, liter per second, gallon per minute, cubic foot per second, CFS. Another term that's related is the flux. This is instantaneous loading rate. I usually don't hear this a lot in terms of water science. Sometimes you'll hear flux used when talking about rivers and nutrient loads traveling down rivers. So I wanted to introduce it. But more importantly is the term flow rate. Discharge is related to flow rate, but it doesn't have the unit of time. Discharge is just the volume of water. For example, 100 gallons passed through that tile outlet last week. Units here are liters, cubic meters, gallons. An interesting nuance for tile drainage or other kinds of even surface drainage are that we often normalize the volume by the drainage area. So if you divide a volume, like cubic meters, by an area, like square meters, you get an equivalent depth. And that's often how we talk about drainage discharge, is not in terms of cubic meters, but rather millimeters or centimeters. This is similar to how we talk about rain in inches. We talk about drainage in the same way, as a depth, either inches or millimeters or centimeters. Next up, the last two on the list are really where we're going with this lesson, load and loss. And these are very important terms because they're sometimes used interchangeably, which is incorrect. I will fess up, even in some of my own papers, I call load what is actually loss. So take note here, load is just the mass of a substance passing a specified point. For example, 100 pounds of nitrogen flowed out of that tile outlet, 100 pounds. So just a unit of mass, kilograms or pounds. Loss is a normalized load. So just like we normalize drainage discharge by the drainage area, we normalize loads by the drainage area. So here we have kilograms per hectare or pounds per acre, and this is called a loss. A good example here is if I have 100 pounds of nitrogen leave my 40-acre field, and then my friend Dan has 150 pounds of nitrogen leave his 60-acre field, you would say, well, Dan had a higher load than Laura because 150 pounds is higher than 100 pounds. But when you do the math and calculate the loss for Laura and Dan, tell me what you find. I'll give you a couple minutes. Pause the video if you need to do that math. 100 pounds from my 40-acre field, 150 pounds of nitrogen from Dan's 60-acre field. Surprise, surprise, the losses are the same. Pounds per acre, there's no difference. Loss is important because this is really the metric that we're going for at the end of our water quality studies. The equation at the top of the screen I'm showing here underpins all of our water quality studies, and it's a generalized form. Concentration times discharge volume gives our mass load. Like I said, I cannot reiterate enough, this equation underpins almost everything that we do in water quality science. And I want to talk a little bit about, well, why do we need actually concentration and flow both? Why do we need to calculate mass loads? Isn't concentration enough or flow enough? Here's some data that I want to use to illustrate this point. These are data from a bioreactor that we were monitoring. In the top graph here, the green or kind of olive colored circles are nitrate concentrations and water flowing into the bioreactor. The open squares are nitrate concentrations in the water leaving the bioreactor. And so just looking at this graph, you might say, well, towards the end of the summer, around September-ish, that bioreactor is working the best that it's ever done for this period. It has a 100% concentration reduction during that period, especially compared to earlier in the summer, early to mid-July, we only have about a 20% concentration reduction. But this is not the whole story. We need to add in flow data. And here you can see the bioreactor wasn't actually flowing towards the end of the summer. We happened to be sampling stagnant water that was standing in the control structures, but there wasn't actually any flow moving through the bioreactor. And so when we go back to our equation, concentration times discharge volume gives us load. And again, load is just kilograms, it's just mass. So what I'm showing here at the bottom is our incremental load of nitrate nitrogen removed. The gray area between the two lines is the load that's removed. And indeed, earlier in this monitoring period, in early July and mid-July, we're indeed removing more mass of nitrogen than we are later in the summer, where we weren't actually cleaning any nitrogen out of the water. So how do we combine concentration and discharge or flow rate data to actually calculate loads and losses? The inherent challenge is that we typically have water sample data less frequently. We typically take water samples or grab samples less frequently than we have discharge data. It's typically pretty cheap and easy to get high frequency flow data, and more time intensive to have high frequency nutrient concentration data. Now, real-time nutrient sensors are changing this game a little bit, but they're still pretty expensive. So let's go to the next lesson and see exactly how we can put concentration and discharge data together.